Well, thank you for joining. My name is Bill Goebel. Obviously, I've worked for Exeter since it was founded as a co-founder. I have a lot of experience in mostly high availability critical hardware design, some experience in software. This is the first of a series of 5 webinars that we're going to be doing this fall on FMEAs. And as part of this, we'll show you a number of different options. We will, of course, mention from time to time the Exeter solution to some of our other problems that we come across. And if you have any interest, of course, don't hesitate to ask. For those of you who don't know us, Exeter was founded in 2000. We are very technically oriented. We're technical geeks. I like the term. I'm proud of it. We do all of our work in functional safety, alarm management, and cybersecurity. And most of our work has to do with control systems, automation systems. I mean, for petrochemical industry, for robotics, for automobiles, for low-speed vehicles, many, many different industries, same fundamental issues. One of our companies, the engineering tools group called Exeter Innovation, does engineering tools. We have one suite of tools at the systems level called Excellentia, and a second suite of tools for product developers called OEMX. And we're not going to really talk about that until the very end, but the OEMX, the ArcX tool, which is part of OEMX, is Exeter's solution. Another one of our companies does certification. Exeter Certification is accredited as a certification body by ANAB in the United States and by INAB in Ireland as a notified body for the EU. We write a lot of books. I told you we're very technical, we're geeks. I'm proud that we've authored a majority of the references for automation, safety, reliability, and cybersecurity. We keep strong, carefully crafted databases of failure rates for devices, which is part of the Excellentia software suite, and for components, which is part of the OEMX software suite. Today, we're going to talk about failure modes and effects analysis, FMEA. One of the kind of problems with FMEA is there's a lot of different definitions in the world. You can read the American Society of Quality definition at the top, but I'm just going to describe it in a very practical way. And FMEA is a very effective design verification technique. Design verification. What's that mean? It's a tool that helps you find issues, problems. It's a systematic procedure that helps us find hidden issues in our designs. It's most effective at the architecture level of a design, where you are crafting a concept through multiple levels. For example, on the right-hand side, there's a controller architecture drawing with input circuits, computing circuits, and output circuits. That's kind of a system-level architecture. Although remember, although we define system as the highest level of interest. And you can see subsystems, which are more detailed. Designs, good designs, are hierarchical, structured designs where you start at the top and work down. In this environment, the FMEA is most effective as a mechanism to systematically find design problems. Now, one of the issues is that I have found, even in the last year, that the term FMEA seems to mean a lot of different things to different people in different industries. It's not a definition that develops common understanding. You can see some of the definitions from some of the other references, including Wikipedia, and they are consistent, but the details of what you put into it and what you get out of it, I've found are very, very different from industry to industry, from standard to standard. And so if and I looked at all these different terms that were used: DFMEA, PFMEA, FMECA, FMEA-MSR, and FMEDA, and I'm wondering, they're not the same thing. Some of them are and some of them aren't, and so just be careful. To make it clear in this webinar, or to make it more clear in this webinar, we're going to focus on a design FMEA done at the architecture design phase of a new product development process. If you have not been involved in a company with a good development process, or if you're thinking about upgrading or modifying, please think about your objectives. New product development is tough, as many of you know, I would bet. You have to balance conflicting goals, and depending on the industry and the marketing and the commercial situation, you may have to balance and sacrifice one of these three goals: time to market, development cost, or safety and reliability. But what we're really trying to do in a good development process is improve all of them and not sacrifice one for the other. We have to ask ourselves, can we achieve a better process that does not require nearly as many trade-offs? Some trade-off is inevitable, at least in my experience. There is a way to optimize and reduce trade-offs. Many experienced engineering managers know that if a problem is found early in the design cycle, that's good, like that green mark on this chart. If you don't find the problem earlier and you follow a path down the development process and discover it very late, worst case in final validation testing, we used to call that system testing, that's a disaster. Why? Because you got to go back and redesign and re-implement and retest. That's costly. And what else? It increases your time to market. Finding a problem early reduces redesign, which reduces development cost and time to market. Yay, that's good. How do you find problems early? The answer is every step in a good engineering process has to have what we're calling a quality verification activity. Was this step carried out correctly? That's the question. And of course, we document that the quality verification check was done via some method. And of course, that documentation then is really great for those who want functional safety or cybersecurity certification, because that's the kind of an information a certification body assessor needs. FMEA is a great quality verification method. Many companies have found the technique to be Very effective. I've been in FMEAs even years ago before we had good tools, where at the end, the engineering manager comes up and says, you just paid for yourself many times over. And that's very good. Makes you feel good. FMEA has been shown to pay for itself many times over by finding problems early. It can be used on hardware and software and semiconductors and FPGAs. The method can even be used for cybersecurity threat analysis. In this example, I have two levels of design. On the left-hand side, I've got the high-level software design for a discrete safety controller, we call it. It has internet messaging capability. It can share variables with peer controllers. It has its own inputs and its own outputs. And it executes user-programmed functions. Now, the user program function block is blown up into a more detailed design in the right-hand side lower corner, which shows a hierarchical design. Now, FMEA can be done at the systems level and is often worthwhile, but quite frankly, it's most important to be done at the lowest level of design, like the one in the lower right-hand side of the screen for software. And the technique has been shown, if you do it properly, to really find potential issues before you even begin a more detailed design and coding. Now, the problem then is with function blocks that aren't designed yet, software that isn't coded yet. How do you know what the failure modes are? You have a block, you know what the function should be. How do you know what potential failure modes are? Well, the procedure is, in general, let's write a quick little note. You list all the functional blocks. For each block, you can use, the common process is to use a set of guide words that were actually created by the chemical industry to analyze hazards in their chemical processes. And we look at the guide words and use them to help brainstorm a list of valid failure modes. Yeah, kind of have to do that, and it depends on what the function of the block is. And then you say, well, what if there is no function? What if I have too much function, more? What if I have not enough of the function? What if I have some other result, or as well as, and you go through all the guide words and use them, the ones that are applicable, and use them to come up with a list of failure modes for this particular functional unit. And then once you have identified the failure modes, and that's where the FM comes from in FMEA, you list the effect of that failure. That's the FME. And that might be fail safe or fail dangerous or degraded operation or whatever's appropriate. And if you want to, you can list the criticality and severity of that effect for priority scheduling. Most of the time at this point, you've recognized that there is a potential problem that you do not want. If this block fails in this mode, that's bad. And so we will take time to brainstorm potential mitigations, or in some standard that's called recommendations. Maybe you want an automatic diagnostic. Maybe you want to put in, change the design so that this particular failure mode can no longer happen. There are many options, which I'll show you in a minute. Now, the problem with this and the complaints that I have gotten from a lot of people over the years is, oh boy, it looks like it's painful to get from a guide word to a functional failure mode. And it can be, and it can be time consuming. And of course, perhaps the most important question is, what if you miss one? Well, if you miss one, you might miss something important. So we try not to do that. But I mean, you look at you pick the ones that seem most relevant and do your best job. Then people ask, well, what about mitigation techniques? Do I have to come up with all those on my own? Well, there are books and references available, but normally speaking, you will be coming up with mitigation techniques for your particular blocks. And then lastly, if you need good documentation, you might ask how to do that. But I will warn you that the results are clearly proportional to the expertise of team members. This whole concept requires some experienced people to be on the team, because they're the ones that have lots of memories and lots of issues and can do a much better job. Now, here's the process. Our objective, of course, number one, is to find design problems early, right now, early in the design. Now, we're going to do that by systematically reviewing all blocks, hardware blocks, software blocks, FPGA, ASICs, all the functional blocks, no matter how they may or may not be implemented. For each block, you identify the potential problems / failure modes. And then, if it is an issue that must be changed, if it's a failure mode that causes an effect that it's unacceptable, you're going to identify what can be done. And you might want to avoid the problem, verify that it cannot happen with analysis or testing, design an automatic diagnostic to detect the problem, and take appropriate action. And finally, maybe you could change the design to make sure it doesn't happen. Objective number 2 of a good FMEA is to produce and document your design. Now, you did document the architecture. You do have a drawing with blocks and a list of the functions, but now you can document the failure modes of each functional unit and the mitigations that have been chosen for those that are unacceptable. You can also take time, it's very valuable right now to take time to define the integration test cases that might help you verify that these potential failure modes cannot happen, or the validation test cases you need to make sure that your mitigations are properly implemented. And of course, all of your recommendations typically will result in new requirements added to your requirements document. So all of this comes out of an FMEA, all of this wonderful documentation. And I use the word wonderful because I think it's wonderful if a tool does the report for me. I'm not a big documentation person myself. And don't forget, if we do a good job documenting the design and the failure modes and the mitigations, that's exactly the information you need, in part, to meet functional safety or cybersecurity requirements for certification purposes. And that can be very nice to get that done. Well, I said FMEDAs are wonderful. They really do a great job. And yeah, they do. But there's some downside. You can look at the slide. I don't know if you've ever been through an FMEA and you got bored and almost fell asleep, but that can happen. Some managers have commented that the engineering hours consumed by an FMEA were quite excessive. I mean, I've got 4 or 5 people in a room for 40 hours. My God, that's 200 engineering hours. We can't afford that kind of time. We got to get moving with the design implementation. Are you sure this is really worth it? And it's the job of a manager to challenge everything and whether it's justified or not. And in some designs, the more complex ones, a very high number of mitigations or recommendations are made. And sometimes if you get a large number, like, 50, 100, you can't deal with all of them. You certainly can't deal with all of them based on your time to market and development cost constraints. So you have to prioritize. So that's the issue we're going to deal with today. We will deal with the first 2 issues in additional upcoming FMEA webinars. An FMECA was named and defined, to my memory, back in the late 80s, early 90s. At least that's when I learned about it. And it was called failure mode effect and criticality analysis because additional variables were added to each failure mode: the severity, the likelihood, and a probability of detection. And each one was given a number from 1 to 10. 1 was the lowest, 1 is okay, and 10 is really bad. And an RPM was calculated by multiplying the 3 numbers and put into a 4th column. Obviously, higher numbers are given priority, and we have to deal with the higher number units, failure modes first. Low number failure modes can probably may be postponed till the next release. All right, I learned about this, and I guess quite frankly, mine were never that complicated, and I didn't feel I needed them, but it's okay if you don't want them. You can leave that blank in most spreadsheets and in many of the tools, but the bottom line is it's there if you want to use it. Now here's how it looks. The severity is how bad is it if this effect occurs? Your product fails in this particular mode. And you can see 10 is really bad and 1 is I don't care. And you pick a number from 1 to 10. That might seem pretty easy. It is, of course, if you have a 1 or a 10, but often it's kind of hard, especially with this description, with any of the descriptions that exist that aren't, quote, numerically calibrated. But you can sit down, and it does consume engineering time if you have to pick a number and then somebody else picks a different number and you have to argue which number is correct. Excuse me, a good facilitator won't let that go on too long, but it does take some time. Same with likelihood. Severity is one thing, but if it's not likely, we'll get a much lower score. And of course, this one's pretty good. It's kind of calibrated with numbers, and it makes it a lot easier, but there's still a lot of debate and a lot of argument about which number to choose. And you have to be careful about how much time you spend debating each of these items. This last one is an interesting one. But if this does occur, can we tell that it happened and take some action? And Maybe is often the answer, or maybe not. It depends, of course, but it's a place where you can document the impact of your automatic diagnostics or your periodic inspections. Or in the case of an automotive, the driver recognition. And you can document how likely it is the problem will be detected. Now, there's a number of issues with this RPM. Number one, I've already mentioned, choosing between the numbers in a range of 1 to 10 seems like it might be easy, but it has been time consuming. And due to debates and arguments, especially if you get someone who's pretty stubborn. Another problem, sometimes the risk numbers are confused. And what I mean by that is sometimes people are thinking about the application of the product, the environment, the use of the product, and not the design. We, in the FMEA, remember, we're talking about an architecture design. And I don't want to know about the risk of the installed product in the system. That should have been dealt with in a whole different mechanism. What we're looking at now is the risk of a design issue, a mistake, a failure mode that is not properly mitigated. And then you have to ask, okay, what are we talking about detection? Are you talking only about automatic diagnostics that detect problem? Or are you talking about operator recognition? And maybe you might want to think about that a little bit. If the operator can detect a problem caused by the design, but if you talk to human reliability experts, there's some very strict criteria for using a high probability of human detection. Are you talking about a periodic inspection? And the answer is, yeah, you could view any of those, but be very careful and don't let that get you confused, and don't let that suck up a lot of engineering hours. I don't want my people sitting there for an extra 5 people sitting in a meeting for an extra hour arguing about stuff that's not essential. Now, what's happened in the world of RPN because of the time-consuming and confusing issue is many companies and even standards eliminate many of the choices and simplify the choices. Fewer choices, faster answer. And some FMEA tools are now simply giving you none, high, medium, or low, which is much easier to deal with in general, at least compared to a number between 1 to 10. Simplify the selection, reduce the engineering hours, and still get the main benefit of establishing priority. Sometimes, and the second issue is sometimes the risk numbers are confused with the product, how it's applied in the application, or the design. And remember, we need to focus on the architecture design at this point in the development process. And the reason is the application level risks are typically analyzed long before the design begins. And that analysis is used to create the requirements for the product you're designing. An analyst can absolutely focus on the design risk, but the easiest way to do that is not be thinking about a number of 110 and having a predefined list of impact. The potential impact of any failure mode comes from a predefined choice list, not from an RPN number or a comment. For example, we're talking about the input circuit for 24-volt power. If the power goes to 0 volts, the 24-volt output voltage feeding the device is close to 0. Now, maybe we don't know yet what the cause might be, but in this case, we've judged that to be a potentially dangerous fault. And it sounds like a 10 if you were estimating RPN severity. You pick the dangerous fault and it goes in and you move on real fast. Good. Detectability for any given mitigation. There is a level of effectiveness. And again, the choice of high, medium, low is the right way to go. And this particular tool associates a quantitative diagnostic coverage using guidance from IEC 61508. And you can use that later on to feed into an FMEDA, which will give you a very precise quantitative measure of detectability. All right. What are we getting so far? Simplify your RPN numbers. RPN numbers are valuable, but they're far more valuable if they're simplified. And right now, a very limited selection of the 1 to 10 numbers or a high, medium, low selection is becoming quite common out in the industry. Now, FMEAs can be absolutely done with spreadsheets. In many cases, I find that this may very well be. I haven't done a market study. You can let me know how you do FMEDAs, by the way, but last I checked, a lot of people were using a spreadsheet. For many years, that's all I used. And you can look at this example spreadsheet and see kind of things that are put into the columns. And what we do at this point is for every function block, we do have to use the guide words to identify the failure modes. That's right here in this second to the left. You could identify the cause if that's useful to you. I generally don't. And fill in the columns that are relevant to your industry and your application along with your RPN numbers. And they use, I see they multiply 2 numbers and add the D. That's the other thing. I do find all different mathematics in all the different standards, but that's okay. Still, RPN numbers still serve their purpose for establishing priority. In addition to spreadsheets, at this point in time, we have evolved to the point where there are many FMEA tools available. Most of them use a format, a square spreadsheet style format, and some of them have code to help you make your selections. Other tools available on the market, you make your selections from pull down lists, and the only chart you get is the FMEA report, which comes out at the end. And this can really speed things up. As our tools get better, the next generation of FMEA tools are working very hard to increase the accuracy. And if you get a good tool suite, you can generate quantitative FMEDA results based on your FMEA. The goal should be to improve the design quality and reduce engineering time. This is not exclusive. We want all of these. which does reduce project development cost. It does expose design errors earlier, which reduces time to market. And it can and does support safety certification. What I really like is a tool that would support hardware, software, functional safety, and cybersecurity, all with the same method and the same commands and the same structure. So that's where the tools are going today. Imagine the difference between a clean sheet of paper or a blank spreadsheet and a tool that gave you context-specific hardware failure modes, proven suggestions for mitigation techniques, FPGA failure modes and mitigation techniques, software failure modes as a function of block type, and effective mitigation techniques based on experienced designers' input, context-specific cybersecurity failure modes, along with cybersecurity mitigation techniques. Even a dependent failure analysis patterns if you're in the world of 26262. Of course, it is important that you can record your own failure modes and your own proprietary mitigation techniques, so that once you enter them into a tool, the tool will show them to the engineers doing subsequent projects. It's a great way to capture corporate intellectual property. Now at Exeter, we call this the Expert Design Knowledge Base. And we have found, as you will see in subsequent webinars, that this kind of thing, this kind of a tool drastically reduces the chance of design error, improves quality, and reduces engineering time, which are the main trade-offs that we want to improve upon. So I conclude that RPM numbers, the FMEA technique, is unbelievably valuable. RPN numbers are very effective in establishing priority when you have a lot of mitigations. But the 10 number RPN system appears in many cases consumes too much engineering time and is being replaced in many companies and in many standards by a reduced set of selections or a simple high, medium, low technique. That makes the RPM system, or the priority system, even more valuable. RPN simplification is important in streamlining an FMEA to reduce the engineering hours. And you probably should have some idea what I'm talking about. It drastically reduces the amount of debate and argument while maintaining and even improving the essential benefits of the priority and the FMEA itself. All next generation FMEA tools, I predict, will have much simplified RPM methods. So I hope you got a good idea of what RPN numbers are about, what FMEA is about, and how simplified RPN numbers really help. Even the 1 to 10 numbers help you when you must prioritize. This webinar was one of 5 that we're planning for this fall. You can see the titles on the others, the abstracts, and more details will be posted on the Exeter website shortly. Again, thank you for your time. Do not hesitate to refer to the many white papers on the Exeter website, or you can send an email to us. Don't hesitate to look at all of our resources. We work very hard to train the world on how to make more reliable and safer products with less development time and shorter time to market. Thank you very much. Have a great remainder of your day. Goodbye.